Welcome all. Now we are discussing theorem 7.25. The statement is if K is compact and if Fn element of C of K for n equal to 1 to 3 etc. and if Fn is pointwise bounded and equicontinuous on K, then we have two results. One is sequence Fn is uniformly bounded on K, and the second is sequence Fn contains a uniformly convergent subsequence. Okay, let us discuss the proof of the first result. And we have the suppositions K is compact, Fn element of C of K for n equal to 1 to 3 etc. and sequence Fn is pointwise bounded on K, and sequence Fn is equicontinuous on K. We have to prove that Fn is uniformly bounded on K. Let epsilon greater than 0, we will choose epsilon positive, and since sequence Fn is equicontinuous on K, by the definition there exists delta positive such that modulus of Fn of x minus Fn of y is less than epsilon whenever d of xy is less than delta and for every n equal to 1 to 3 etc. This is the definition of equicontinuity, and let it be equation number 1. Now consider all open balls with radius this delta. Okay, that will clearly form an open cover for K, and we know K is compact, so it has a finite subcover. Say UP1 delta, UP2 delta, etc. UPR delta for some points P1, P2, etc. PR in K. That is, there are some finite number of balls whose union can cover K. Okay, let choose X element of K. Then X is an element of one of the balls mentioned above, that X element of UPI delta for some pi I equal to 1 to R, that is x will be in the first ball or the second ball or in the rth ball, wherever it is. Okay, this means that distance, that is d of x with pi is less than delta for some pi, and so by equation 1 we can write that modulus of Fn of x minus Fn of pi is less than epsilon. Let it be equation number 2. And we know that sequence Fn is pointwise bounded, and so for these elements also, what P1, P2, etc. PR, these are also elements of K, and for these elements also Fn is pointwise bounded. So there exists natural numbers or real numbers m1, m2, etc. mr, such that modulus of Fn of P1 is less than m1 for every n, and modulus of Fn of P2 is less than m2 for every n, etc. Modulus of Fn of PR is less than mr for every n. Choosing capital M with a maximum of all these m1, m2, etc. mr, we can write this relation is true for every I equal to 1 to R. That is, modulus of Fn of Pi is less than m, which is the maximum, for every n and for every I equal to 1 to R. That is, this is true for every P1, P2, etc. PR. Let it be equation number 3. Now we are going to the main portion, that is, we have to prove that Fn is uniformly bounded on K. So we are checking modulus of Fn of x. Now modulus of Fn of x is equal to modulus of Fn of x minus Fn of Pi plus Fn of Pi. That is, we are adding and subtracting a term Fn of Pi, and by the properties we can write this like less than or equal to modulus of Fn of x minus Fn of Pi plus modulus of Fn of Pi, and we know that this first term is less than epsilon by equation 2, and the second term is less than m by equation number 3. So we have obtained modulus of Fn of x is less than epsilon plus capital M, where epsilon is a quantity that we have chosen and m is a natural number or real number which is a bound, clearly that is a constant. So m plus epsilon is a constant, and so modulus of Fn of x is less than epsilon plus m for every x element of K and for every n equal to 1 to 3 etc. means that sequence Fn is uniformly bounded on K. That is, there is a bound epsilon plus m for every functions Fn and for every x element of the compact set K. So this is clear proof of sequence Fn is uniformly bounded on K. Now we will discuss the part proof of the second result. That is, we have to prove that Fn contains a uniformly convergent subsequence. Okay. Since we have the supposition K is compact, considering an open cover consisting of all open balls with radius 1 by n, clearly it has a finite subcover since K is compact, whose union covers K. This is true for every natural number n. So we are considering n very large, and we will get a countable dense subset capital E of K by choosing n very large. Okay, so let E be the countable dense subset of K, and since sequence Fn is pointwise bounded on K, it is pointwise bounded on E also, which is countable. So by theorem 7.23, this sequence Fn has a subsequence Fni such that Fni of x converges for every x element of the countable set E. Okay, we shall prove that this subsequence Fni converges uniformly on K. For that, choose epsilon positive, and since sequence Fn is equicontinuous on K, there exists delta positive such that modulus of Fn of x minus Fn of y is less than epsilon by 3. We are taking here also for our sake that epsilon by 3 whenever d of xy is less than delta, and for every n equal to 1, 2, 3, etc. Let it be equation number 4. Now consider the open balls with center points in E and radius this delta. Okay, that will form clearly an open cover for K since E is dense in K. Since E is dense in K, the points of E are the points of E are everywhere in K, and so we can see that will form an open cover for K. And since K is compact, this open cover has a finite subcover, say ux1 delta, ux2 delta, etc., uxm delta for some points x1, x2, etc., xm in E. Clearly, K is contained in the union of these open balls. Let it be equation number 5. And we know that sequence Fni of x converges for every point in E, and so for these points x1, x2, etc., xm also. So by definition, there exists for the same epsilon positive we are mentioned above, there exists natural numbers n1, n2, etc., nm such that modulus of Fni of xs minus Fnj of xs less than epsilon by 3 for every ni nj greater than or equal to ns for s equal to 1, 2, etc., m. Okay, let n be the maximum of all these n1, n2, etc., nm. Then we can write this equation, hence we can write this inequality is true for every s equal to 1 to x n. That is, modulus of Fni of xs minus Fnj of xs is less than epsilon by 3 for every ni nj greater than or equal to this capital N, which is the maximum of all ni's for s equal to 1 to etc., m. So this is true. This inequality is true for every points x1, x2, etc., xm. Let it be equation number 6. Okay, if we choose a point x from K, then by equation number 5, x is belonged to one of the open balls uxi delta. Let it be uxs delta. Okay, that is, x is an element of uxs delta for some s by the equation number 5. That means the distance of x with xs is less than delta, and so by equation number 4 we can write modulus of Fni of x minus Fni of xs is less than epsilon by 3 for every ni. Let it be equation number 7. Then we are coming to the main point. It follows that modulus of Fni of x minus Fnj of x equal to, now we are adding and subtracting some terms like Fni of xs and Fnj of xs, and we are splitting the inequality into 3 terms, and we found that these 3 terms are less than epsilon by 3 by equation number 6 and 7 for every ni nj greater than or equal to capital N. That is, modulus of fni of x minus fnj of x is less than epsilon for every ni nj greater than or equal to capital N and for every x element of k. So by theorem 7.8 we can conclude that sequence fni converges uniformly on k. So we have proved that sequence fn contains a subsequence which is uniformly convergent. Okay, this is the theorem. Thank you.